In the last chapter we studied two things. We studied parameterized curves and we studied vector fields. So here's an example of both in the same picture. Imagine that you're running on a track. So this path, which you could parameterize, represents the track. Now imagine that as you're running on the track, there's a wind. And so this vector field represents the wind. As you run around the track, the wind does different things to you. As you're running on the home stretch, the wind is to some extent at your back, and so to some extent pushes you forwards and helps you move forward. As you come around the backside, the wind is more in your face and so is against you. And so we'd like to measure that effect of the wind on your trajectory around the path. Along the home stretch, the wind should have the effect should be measured as positive. It's moving you forward. If the wind were pointing more directly with the track, it should have a stronger effect than the wind that I've shown in blue. But the net effect should be positive. Along the back stretch, the wind is in your face, and so the net effect should be negative. So this idea is measured with a line integral. It measures the extent to which an oriented curve, the track, agrees with the direction of a vector field, the wind. If the curve closely follows the vector field, then the corresponding line integral should be positive and large. So if it were the blue wind, I would have a larger line integral value than the red wind, which is quartering, but still positive. Whereas along the back stretch, I should have a curve that's in the opposite direction of the vector field, and the corresponding line integral should be negative and large depending on the extent to which the wind is in your face. If the curve is perpendicular to the vector field, so that is in between behind you and in front of you, then the line integral should be 0. So for example, right over here on this section where the wind is perpendicular to your path, the line integral should be 0, and the same thing on this corner up here. Okay. So how do we measure the extent to which a path and a vector go in the same direction? Well, a dot product. Remember that the dot product of two vectors that are perpendicular, if I take two vectors and they're perpendicular, their dot product is positive. If they point in the same direction, then their dot product is as large as possible, because remember A dot B, one of its definitions is the magnitude of A times the magnitude of B times the cosine of the angle between them. So if they're in the same direction, the angle is 0, and cosine of theta is as large as possible. Here's the idea mathematically. Here's a curve C, so this is the curve, and this curve is inside a vector field, so these arrows represent the vector field. So we need a little bit of structure here. So suppose this is the origin, and every point along this curve I can determine with a position vector. So this first point is the position vector r0, this would be the position vector r1, and here's the position vector for r sub I plus 1. So the idea is going to be to break down this curve into small pieces. So this piece would be delta r. Okay, so that's a change from this position vector to this position vector. That's how much the position vector changes. Okay, so ultimately we're going to let the size of those change in position vectors get smaller and smaller, as we've seen in many other examples in calculus, and take the dot product of that change in position vector times the value, or dot it with the value of the vector field at that particular point. So we take the dot product of this change in position vector with this value of the vector field at that point. And if we look at small enough delta r, that should be constant. We can pretend that it's constant. We take all these dot products, we add them up all the way along the curve. So we're going to add them all up, and then we let the size of each change in position vector go to 0. That's the definition of a line integral. And that does exactly what we want it to do if you think about the track example on the previous slide. Here's a first example just to get the idea of what's going on. So the arrows represent a vector field. Notice that they only have I components, they have no J component, and they get larger the further away I get from the x-axis. And here's the path that I'm going to follow, this semicircle that goes from some point on the y-axis to the origin along a curve. So two things happen, actually three things happen. Up here at the top, the curve is going generally in the direction of the vector field and in the same direction. So up here, the contribution will be positive. On the other hand, at the bottom end of this trajectory, I'm going generally against the vector field, but the vector field is smaller. So down here, I should get a negative contribution. However, this positive contribution will be larger because the value of the vector field is larger than the negative contribution. And here in the middle, notice that the curve is roughly perpendicular to the direction of the vector field. So in here, roughly, the contribution should be 0. Okay, so we've got 0 in the middle, big and positive at the top, small and negative at the bottom. So the value of this line integral, the integral of the vector field dot dr, overall should be positive. Here's the first algebraic example. We want to find the value of the line integral where the vector field is given by x times j, so it only has j components, the vector field, no I components, and c is the line segment from the point 2, 0 to the point 2, 5. So first let's think a little bit about what the vector field looks like. It has only j components, so it's going to point only in the y direction, and as x gets larger and positive, the vector field should get larger, whereas if x is negative, the vector field will point in the negative j direction and get larger the farther x is away from the origin. The path starts at the point 2, 0 and goes up to the point 2, 5. So it's going to go up to 5. So there's the path, and it's important to notice the direction. So notice the direction of the path is the same as the direction of the vector field at x equals 2, and so the line integral should certainly be positive. Now, we can simplify this problem quite a bit. Notice that on this path, x is always 2. So if x is always 2, then the value of the vector field is simply 2j everywhere. Okay. Also, we want to think about the change in position. And notice this is a vector. So delta r is a small piece of this path. And we're going to rewrite this delta r a little more precisely to be helpful. Notice that each of these delta r's also points only in the j direction, and its length I'm going to write more descriptively as delta y. Okay, so the length of one of these paths, one of these small incremental paths, is delta y. It moves in the y direction, and it points in the j direction. Okay, so the line integral, remember, from the definition, is equal to a sum of f dot delta r. Okay, and then I let the delta r's, the size of the delta r's, go to 0. Well, let's think about f dot delta r for just a minute. This is, in this case, 2j dotted with delta y j. And so when I take that dot product, I simply get 2 times delta y. So this sum, f dot delta r, simply turns into a sum of 2 times delta y. So let's distribute out the 2, and I get the sum, or 2 times the sum of the delta y's. Now, as delta y goes to 0, as delta y goes to 0, this sum is simply the length of the path. So this sum, as delta y goes to 0, is 2 times the length of the path. Well, the length of the path is easy. If we go from the point 2, 0 to 2, 5, that length is simply 5. So this is 2 times 5, or 10. So finally, the line integral of the vector field f dot dr is equal to 10. And notice that something very, very special happened here. The path was everywhere exactly the same direction as the vector field. Further, the vector field was constant. And so things turned out very nicely. Here's a second example. Again, we want to find the line integral. And the vector field is xi, so this time the vector field has only an I component. And our path is going to go from the point 2, 0 to the point 6, 0. So first let's get a general idea what the vector field looks like. If x is small and positive, then the vector field points in the positive I direction. And as I gets larger, as x gets larger, the vector field is larger, so I'll represent that by drawing larger vectors. And it doesn't matter so much in this example, but if x is negative, the vector field is going to point in the negative I direction, and small when we're close to the y-axis. And as we get farther away from the y-axis, the magnitude of the vectors will get larger. Okay, so there's the vector field. And now the path that we're interested in goes from the point 2 to the point 6. So the path is going to go in that direction from 2, 0 to 6, 0. So our strategy is going to be the same as before. Notice that this time the vector field is not constant. The vector field is x times I, and x changes along this path, so it's not constant. So I'll just leave that alone. But let's think about delta r, the position vector, the change in the position vector again. This time, these vectors have only an I component. The path goes only in the I direction. And so I'll write delta r as some vector with an I component only, and a small bit of this path will be given by delta x. Okay, so f dot dr, f dot delta r, in the definition of the line integral, if I dot these two things together, xi dotted with delta xi is x delta x. Okay, so the line integral of this vector field will then be, well, it's a sum of this dot product, x delta x, and I let delta x go to 0. And if I do that, if I think about this as a Riemann sum, then this becomes the integral of x dx. And the x values, well, the x values go from x equals 2 to x equals 6. So I integrate from 2 to 6. And now I've turned this into a simple integration problem. I integrate x, which is 1/2 x squared, evaluate that from 2 to 6, and we get 1/2, 6 squared is 36, minus 2 squared is 4, and 36 minus 4 is 32, divided by 2 is 16. And that then is the value of the line integral.